So the next topic is scope. So one of the important factors in understanding variables is scope. So we talked about this variable names, then their binding, okay, then lifetime. All these terms we have discussed earlier. Now, another important factor in understanding variables is the scope. Okay. So the scope of a variable is the range of statements in which the variable is visible. Okay. So that is a range of statements in which the variable is visible, where we can access this variable. Okay. So a variable is visible in a statement if it can be referenced in that statement. If we can refer that variable inside that statement, then we can say that the variable is visible in that statement. Okay, so that is the visibility. So suppose we can access that particular variable that is visible. And we have this scope rules. So scope rules of a language determine how a particular occurrence of a name is associated with a variable, or in the case of a functional language, how a name associated with an expression. Okay, so we have for each language, uh, it will have some scope rules, and these scope rules are used to determine how a particular occurrence of a name is associated with a variable, or in the case of a functional language, how a name is associated with an expression. So, in particular, scope rules determine how references to variables declared outside the currently executing subprogram or block are associated with their declarations and thus their attributes. So, these scope rules means they will determine how references to variables declared outside the currently executing program or block are associated with. So suppose we have a subprogram and we have some references to variables, and these variables are declared outside the subprogram. Okay. So this scope rules will determine how this reference can be done. Okay. So a clear understanding of these rules for a language is therefore essential to the ability to write or read programs in that language. Okay, so we should have a clear understanding of these rules. Then only we'll get the ability to write or read programs in that language. So if we want to write programs in C language, then you need to know, or you need to have a clear understanding of the scope rules of the C language. Okay. So a variable is a local in a program unit or block if it is declared there. Okay, so we know that if we have a program unit or if we have a subprogram or a function, then if a variable is declared there inside that subprogram, then we can say that the variable is local to that particular subprogram. Okay. And the non-local variables of a program unit or block are those that are visible within the program unit or block but are not declared there. Okay. So non-local variables means their declaration will be somewhere else, not inside that particular program unit. But we can refer or we can use these variables. Okay. That is known as non-local variables, and global variables are a special category of non-local variables. Okay, so global variables means they will be visible to all the program units inside the program. Okay, so that is a special category of non-local variables. So when we talk about this scope of variables, so that is what is meant by scope. How can we refer that? That is the place or the statements, set of statements where this particular variable is visible. That is known as the scope. Okay, or the range of statements in which the variable is visible. That is known as scope. And we can have basically two types of scope, that is static scope and dynamic scope. So we'll see this static scope first. So Algol 60 language that introduced the method of binding names to non-local variables called static scoping. Okay, so binding names to non-local variables. So we have non-local variables, that is variables declared outside this particular program unit, and we are binding names to this non-local variables, that is known as static scoping, and which have been copied by many subsequent imperative languages and many non-imperative languages as well. Okay, so Algol 60 introduced this static scoping, and many other languages, subsequent languages actually copied this concept from Algol 60. And statiscoping is so named because the scope of a variable can be statically determined, that is prior to execution. Okay, so scope of a variable can be statically determined. So this permits a human program reader and a compiler to determine the type of every variable in the program simply by examining its source code. Okay, so that means we'll be able to determine scope of a variable prior to execution. Okay, so that is if we have a program with us, then simply examining this source code, we'll be able to tell or we'll be able to determine the type of every variable in the program. Okay, so there are two categories of static-scope languages. Okay, those in which subprograms can be nested, so which creates nested static scopes, and those in which subprograms cannot be nested. Okay, so we have, when we talk about the static scoping itself, it has two categories. One is the case with nested subprograms. Okay, so we'll have nested static scopes, and the other one is where we the subprograms cannot be nested. So in the latter category, static scopes are also created by subprograms, but nested scopes are created only by nested class definitions and blocks. Okay. So in the second one, where we do not have this nested subprograms, static scopes can be created by subprograms, but nested scopes are created only by nested class definitions and blocks. Okay, so we do not have this subprograms or nested subprograms. So, some languages like Ada, JavaScript, Common Lisp Scheme, Fortran 2003 plus, and some Python. All these allow nested subprograms, but we know that the C-based languages do not allow this nested subprograms. Okay, so when this a reader of a program finds a reference to a variable, the attributes of a variable can be determined by finding the statement in which it is declared. That is either explicitly or implicitly. So it means that when the reader of a program finds a reference to a variable, so we have a variable and we have some reference to a particular variable inside a program unit. So then how we can determine the attribute of that particular variable? Attributes like its value or its type, etc. or its scope, its lifetime. So how the attributes of this variable can be determined? This can be determined by finding the statement in which it is declared. Okay, so inside the declaration but only we have a type of a particular variable or its value, etc. So that can be determined by finding the statement in which it is declared. So in static scoped languages with nested subprograms, this process can be thought of in the following way. Okay, so we have static scope language with nested subprograms. So suppose a reference is made to a variable x in subprogram sub 1. So we have variable x and a reference to x is made in sub 1. So the correct declaration is found by first searching the declarations of subprogram sub1. Okay. So when we have a reference to a particular variable in subprogram sub1, what we first do is we'll search for a declaration inside this sub1 for this particular variable x. So if no declaration is found for the variable there, the search continues in the declarations of the subprogram that declared subprogram sub1, which is called its static parent. Okay. So suppose that this particular variable x is not declared inside subprogram sub1, then we will search for the next enclosing procedure of this particular sub1. That is known as the static parent of sub1. Okay. And if a declaration of x is not found there, also, then the search continues to the next larger enclosing unit. Okay, that is the unit that declared sub one's parent. Okay, so and so forth. We'll continue like this until a declaration for X is found or the largest unit's declarations have been searched without success. Okay, so in that case, suppose this particular variable is not declared anywhere. Okay, so in that case, an undeclared variable error is reported. Okay, so the static parent of subprogram sub1 and its static parent and so forth up to and including the largest enclosing subprogram are called the static ancestors of sub1. Okay, so we have a nested subprograms here. We have a static scoped language and which supports this nested subprograms. So there, what we are trying to do is we are searching for or we have a reference to a variable x inside the subprogram sub1. Suppose this sub1, immediately what we can do is we can search for a declaration of this x inside this sub1. If that is not seen, then we'll search for the enclosing procedure or enclosing subprogram of sub1. That is known as static parent of sub1. Okay, if that is also not there, that is declaration for X is also not there in static parent of this sub1, then it will look for the static parent of this particular static parent of sub1. Okay, we will keep on doing like this until we get either we'll find out some declaration for x. In that case, everything is fair. But if no declaration is found like that, then what we can do is an undeclared variable error will be generated. And all these enclosing procedures, okay, all these are known as static ancestors of this sub1. Okay. Static ancestors of the sub. So we'll see following JavaScript's function big. Name of that function is big, in which the two functions sub1 and sub2 are nested. Okay, look at this function big. It has a function sub1 and there is a declaration for definition for the sub1 that includes it has a variable x with value 7 and it calls sub2. Okay, and function sub2 is defined here that takes or that has a variable y and that will contain value of this variable x. And after that, we have inside this big function, we have variable x equal to 3 and that calls sub1. Okay. So, suppose we have this static scoping. So, the reference to variable x in sub2, we have a reference to variable x in sub2 and that is to the x declared in the procedure. What is that procedure? Big. Okay. This is true because the search for X begins in the procedure in which the reference occurs, that is sub 2, but no declaration for X is found there. So suppose we have or we see this X inside this sub 1, it will sub 2, it will search for a declaration for X inside this sub 2. That is not there. Okay, so then what we can do? We'll search for the enclosing procedure which has a declaration for this X. Okay, so where we'll see the declaration is sub 1 an enclosing procedure for this sub 2? No, because sub 1 starts here and that ends here. Okay, there is a call to sub 2, but sub 1 is not an enclosing procedure for sub 2. So it will look at the enclosing procedure for sub 2 is big because this sub 2 is declared inside this procedure big. Okay, so it will look at this big procedure or function big where it will find out declaration for this X. Okay, suppose sub2 doesn't have a declaration for this X, then it will search for its static parent of this sub2, that is the big. Okay, where the declaration for this X is found. Okay, the X declared in sub 1 is ignored because it is not in the static ancestry of sub 2. Okay, so sub 1 is not an ancestor of sub 2 because it starts here and ends here. Okay, so this is sub 1 cannot be considered as an ancestor for the sub 2. So whatever declared inside this sub 1 will be ignored inside sub 2. Okay. So in some languages that use static scoping, regardless of whether nested subprograms are allowed, some variable declarations can be hidden from some other code segments. For example, we have the function big in this JavaScript. So there the variable x is declared in both where in big and sub 1 which is nested inside big. Okay, so this sub 1 is nested inside big. So within sub 1, every symbol reference to x is to the local x. Therefore, the outer x is hidden from sub 1. So this is a classic example here. So what we say is, even though we have nested subprograms, we can have some variable declarations hidden from some other code segments. So here we have a variable x and this variable x is defined inside this big and sub 1 and sub 1 is actually a nested procedure within this big. Okay, so when we have a reference to x inside this sub the sub 1, okay, sub 1 we have a reference to this x and a variable x equal to 7. Okay, there this variable is local to this particular sub 1 and variable x equal to 3 that is hidden inside this particular subprogram sub 1 because it has a redefinition for x, so this will be hidden inside this sub 1. Okay. And in some languages like Ada, hidden variables from ancestor scopes can be accessed with selective references, which include the ancestor scopes name. Okay, so in ADA, for example, a function big were written in ADA, the x declared in big could be accessed in sub 1 with by the reference big dot x. Okay, so if it is in ADA language, we can have this hidden variables or we can access this hidden variables from the ancestor scopes using some selective references like big dot x that is possible inside sub 1 where big dot x will not be this variable x equal to 7, that is inside this big procedure big that will have value 3. So now we look at blocks. So when we talk about this scopes, we should consider this block also. Okay, we can talk about the subprograms and blocks also. So many languages allow new static scopes to be defined in the midst of executable code. That is, this powerful concept introduced in Algol 60 allows a section of code to have its own local variables whose scope was minimized. So such variables are typically stack dynamic. So their storage is allocated when the section is entered and deallocated when the section is exited. And such a section of code is called a block. So we have a section of code where it has its own local variables. So scope of this local variables will be inside that section only. And these variables are stack dynamic variables. So their storage is allocated when the section is ended and the storage will be deallocated when the section is exited. So that is known as a block. So blocks provide the origin of the phrase block structure language. So the C-based languages allow any compound statement, the statement sequence surrounded by matched braces. Okay, that will have any compound statement to have declarations and thereby define a new scope. And such compound statements are called blocks. Okay, so we have, suppose in C language we have any compound statement, that is a statement sequence within this curly brackets. Okay, that is known as a compound statement. And these declarations are allowed in these common statements can have declarations and that will define a new scope. So inside this curly brackets, we can have declarations for variables, and thereby we can define a new scope for that variable because the scope of that variables declared inside that curly brackets will be within that curly braces only. Okay. So such compound statements are called blocks. So suppose a list where an integer array, we can write like this: if list of I is less than list of j, then int temp is equal to list of I, list of I equal to list of j, and list of j equal to temp. So we just swap the values. So scopes created by blocks, which could be nested in larger blocks, are treated exactly like those created by subprograms. Okay, so this scopes created by blocks, that is exactly like subprograms. Okay, so references to variables in a block that are not declared there are connected to declarations by searching enclosing scopes, blocks or subprograms in order of increasing size. Okay, suppose we have references to variables in a block, and if that is not declared inside that block, then we can have this enclosing scopes, that is blocks or subprograms in order of increasing size. We'll keep on doing or searching like this. Okay, so consider the following skeletal C function. We have void sub, that is a function, then int count, while some condition, int we declare int again here and count plus plus. So the reference to count in the while loop. Okay, so inside this while loop, references to this count is to that loop's local counts. When count plus plus, that means this particular count. Okay, so in general, a declaration, which means we have a declaration for this count inside this procedure or function sub, and that is actually hidden inside this block. Okay, or inside this while loop. So in general, a declaration for a variable effectively hides any declaration of a variable with the same name in a larger enclosing scope. This kind of a statement is legal in C and C++, but this is illegal in Java and C Sharp. And the designers of Java and C Sharp believed that the reuse of names in nested blocks was too error prone to be allowed. Okay, so what the designers of this Java and C Sharp believed that if we reuse the names in nested blocks, it will or the program will have more errors. That's why they didn't include that. So although this JavaScript uses static scoping for its nested functions, a non-function blocks cannot be defined in the language. Okay, suppose we have non-function blocks that cannot be defined in the language. And most functional programming languages include a construct that is related to the blocks of imperative languages, usually named let. So we have a most functional programming has a construct like let, and that is related to blocks of the imperative languages. So these constructs have two parts. The first of which is to bind names to values, usually specified as expressions. And the second part is an expression that uses the names defined in the first part. Okay. Programs in functional um, languages are comprised of expressions rather than statements. So the in language like scheme, therefore a final part of a let construct is an expression rather than a statement. Okay, so we have two parts for that. First part is used to bind names to values, okay, usually specified as expressions. Second part is that uses the names defined in the first part. That will use the names that is declared or defined in the first part. So final part of a let construct will be an expression rather than a statement. So in scheme language, scheme is a functional programming language. So in scheme language, a let construct is a call to the function let. Okay. So with the following, we have a form for this let. That is let name 1, expression 1, etc. Name n, expression n, and we have by default we have. So what is meant by that? We have this n expressions here. So these n expressions will be evaluated first, and their values will be assigned to the associated names. Expression 1 will be evaluated, and that value will be assigned to name 1, etc. Okay. Then the final expression is evaluated, and the return value of let will be that value, this expression. This will be evaluated finally, and that will be the return value for this let. Okay. So this differs from a block in an imperative language in that the names are of values. They are not variables in the imperative sense. Okay. So here name is values, they are not variables. Once set, they cannot be changed. That is the peculiarity. So however, they are like local variables in a block in an imperative language in that the scope is local to the call to let. Okay, so these variables are like, or these names are like local variables in a block in an imperative language. In that the scope is also local to that particular let. The scope will be local to this particular let only. So next, we can have different kinds of declarations also for different languages, and we'll just look at the declaration order. So in C89 as well as in some other languages, all data declarations in a function except those in nested blocks must appear at the beginning of the function. Okay. So in C89 and in some other languages. So all these data declarations in a function, except those in nested blocks, must appear at the beginning of the function. So some languages, for example, C99, C++, Java and JavaScript, or even C Sharp, they allow declarations to appear anywhere a statement can appear in a program. So declarations may create scopes that are not associated with compound statements or subprograms. So these declarations may create, when we declare variables, that will create scopes that are associated with compound statements or subprograms. So in C++ or in C99 or in Java, the scope of all local variables is from the declarations to the ends of the blocks in which those declarations appear. So there the scope will be local to that particular block only. In C sharp, the scope of any variable declared in a block is the whole block. Okay. So regardless of the position of the declaration in the block, as long as it is not in a nested block. So if in languages like C sharp, the scope of any variable declared in a block is the whole block. So the same is true for methods also. Okay, note that C sharp still requires that all variables be declared before they are used. That is the condition. Okay, therefore, although the scope of a variable extends from the declaration to the top of the block or subprogram in which the declaration appears, the variable still cannot be used above its declaration. Okay, so we can use the variable after declaring them only. So we cannot, the variable cannot be used above its declaration. That is the declaration order. So in JavaScript, local variables can be declared anywhere in a function, but the scope of such a variable is always the entire function. In JavaScript, you can declare it anywhere. Scope is in a scope of this particular variable is always the entire function. Okay. If used before its declaration of the function, such a variable has the value undefined. Okay. So if you use before the declaration in the function, its declaration in the function, such a variable has a value undefined because its value has value will come, value is yet to come. Okay, so the four statements in of C++, Java, and C sharp allow variable definitions in their initialization expressions. Okay, so that we know there in this variable definitions will be there in the initialization expressions in four statements for in I equal to 0 like that. Okay, so in early versions of C++, the scope of such a variable was from its definition to end of the smallest enclosing block. So in the standard version, however, the scope is restricted to the for construct as in the case with Java and C sharp. So again consider the method void fun for int count is equal to 0, count less than 10, count plus plus. So in later versions of C++ as well as in Java and C sharp, the scope of count is from the for statement to end of its body. Okay, so for this count can be used inside this for block inside the or for statement to end of its body. Okay. Now we can define the global scope also. So some languages, including C, C++, PHP, JavaScript, and Python, that allow a program structure that is a sequence of function definitions in which variable definitions can appear outside the functions. Okay, that is a global scope. Okay, so that is definitions outside functions in a file create global variables which potentially can be visible to those functions. And C and C++ have both declarations and definitions of global data. Declarations specify types and other attributes but do not cause allocation of storage. Remember that. Okay. So they will specify types and other attributes but do not cause allocation. Definitions specify attributes and cause storage allocation. Okay, suppose we have declaration that is not going to allocate storage. When we have definition that will specify attributes and that cause storage allocation. For a specific global name, a C program can have any number of compatible declarations but only a single definition. Okay, so we can have different compatible declarations, but it can have a single definition. So a declaration of a variable outside function definitions specifies that the variable is defined in a different file. Okay, suppose we have a declaration of a variable outside the function definitions that specifies the variable is defined in a different file. Okay, so a global variable in C is implicitly visible in all subsequent functions in the file, except those that include a declaration of a local variable with the same name. So suppose we have a global variable in C that is implicitly visible in all subsequent functions in the file if we have a global variable, except those that include a declaration of a local variable with the same name. Suppose we have a global variable in C that is visible in all subsequent functions, but suppose in some function there is a declaration for a name or for a variable with the same name as a global variable. Then uh, uh, inside that function, the definition or declaration will be local to that function only. Okay, there the global definition or global variable will not be effective. Okay, so a global variable that is defined after a function can be made visible in the function by declaring it to be external. Okay, so we have defined a global variable after a function can be made visible in the function by declaring it to be external. Extern int sum. Okay, so in C99, definitions of global variables usually have initial values. So declarations of global variables never have initial values. If the declaration is outside function definitions, it need not include the extern qualifier. So definitions should have initial values. Declarations need not have or never have initial values. So this idea of declarations and definitions carries over to the functions of C and C++, where prototypes declare names and interfaces of functions but do not provide their code. Function definitions, on the other hand, are complete. So you know the difference between declarations and definitions. Okay, so declaration are actually we have prototypes that declare names or interfaces of functions, but that will not provide their code. Then we'll move on to how to evaluate this static scoping. So static scoping provides a method of non-local access that works well in many situations. However, it is not without um, its problems. So we have when we use this static scoping, it has some problems with them. The first, in most cases, it allows more than to both variables and subprograms than is necessary. Okay, so if we have static scoping, it allows more access to both variables and subprograms than is necessary. It is simply too crude. a tool for concisely specifying such restrictions. Second, and perhaps more important, is a problem related to program evolution. Okay, software is highly dynamic, which means programs that are used regularly continually change. So these changes often result in restructuring, thereby destroying the initial structure that restricted variable and subprogram access. So to avoid the complexity of maintaining these access restrictions, developers often discard structure when it gets in the way. So thus, getting around the restrictions of static scoping can lead to program designs that bear little resemblance to the original, even in areas of the program in which changes have been made. So designers are encouraged to use far more globals than are necessary. So all subprograms can end up being nested at the same level in the main program using globals instead of deeper levels of nesting. So moreover, the final design may be awkward and contrived, and it may not reflect the underlying conceptual design. Okay, so that is the case with evaluation of the status copy. It has lots of problems. It is that works well in many situations, but it has lots of problems. And we discussed about some of the problems also. So that is it allows more access to variables and subprograms, and then that problem that is related to program evolution. Okay. So that is programs that are used regularly continually change. So these changes often result in restructuring. So if we need to restructure our programs, it will destroy the initial structure that restricted variable and subsequent access. So that is the main problem with the static scoping. Okay. So now we move on to dynamic scope. So the scope of variables in APL, Snowball 4, and the early versions of Lisp is dynamic. Okay, Perl and Common Lisp also allow variables to be declared to have dynamic scope, although the default scoping mechanism in these languages is static. So dynamic scoping is based on the calling sequence of subprograms, not on their spatial relationship to each other. Thus, the scope can be determined only at runtime. So that is how these subprograms are called or executed, in which order. So that will determine a scope of these variables. So consider the function dict again. So we have sub1, sub2 and variable x and y. Here z is also there. So assume that the dynamic scoping rules apply to non-local references. The meaning of the identifier x referenced in sub2 is dynamic. It cannot be determined at compile time. Okay, so we have an x here and its scope is the meaning of the identifier x inside this sub2 is dynamic. So we cannot determine it compile time. It at compile time. So it may reference a variable from either declaration of x depending on the calling sequence. Okay. One way the correct meaning of X can be determined during execution is to begin the search with the local declarations. So this is also the way the process begins with the static scoping, but that is where the similarity between the two techniques ends. So when the search of local declarations fail, the declarations of the dynamic parent or calling function are searched. If a declaration for X is not found there, the search continues in that function's dynamic parent and so forth until a declaration for X is found. If none is found in any dynamic ancestor, it is a runtime error. Okay. So when a reference to a variable inside some function occurs, this variable will be searched inside that function. If that is not found there, then it will be looked, or we'll look at the function which called this particular function. Okay, so we'll keep on following the calling sequence. Okay, so there may be other function that calls this particular function, and we keep on doing like this until we get, or until we find this particular x. If no x is found, then that is a runtime error. Okay, and again we can consider two different call sequences for sub2. Suppose big function big calls the sub1 and which calls sub2. So the search proceeds from the local procedure sub2 to its caller sub1 where a declaration for x is found. So the reference to x in sub2 in this case is to the x declared in sub1. Okay. Next, sub2 is called directly from big. So in this case, the dynamic parent of sub2 is big and the reference is to x declared in sub in big. Okay. So suppose we have static scoping. In either calling sequence discussed, the reference to x in sub2 would be to bits x. That is the difference between static and dynamic scoping. Suppose inside this we have a function big, and suppose this big calls sub1. Okay, and suppose this sub1 calls sub2. Then suppose we have variable x inside sub2, then what it will search? So it will search for occurrence of or declaration of or definition of this x. Okay, that is there in the dynamic parent of this sub2. Sub2 is called by sub1. So sub1 has a definition for this x that will be taken. Okay, clear. And if big also calls sub2, in that case, this y variable y is equal to x. So we have two calling sequences. One is we have big calls sub1 and sub1 in turn calls sub2. So inside the sub2 we have a variable x. So we'll search for a declaration or definition for x in sub2 that is not there. So we'll look for the calling sequence, that is the procedure or function which call this sub2, that is sub1. So sub1 has a definition for this x, so that will be taken. If big calls sub2, another calling sequence where this big calls sub2. In that case, we look for this, when we look for this variable x, that is available here inside this big variable x equal to 3. So that value will be taken here. Okay. So depending upon the calling sequence, the value for x will change. But if we have a static scoping, as we saw earlier, what was that? The declaration for this x or this value of this x will be from this variable x, that is from this big only, because that is the enclosing procedure for sub2. Okay, so that is the difference between these two. Then we look at the evaluation of dynamic scoping. So the effect of dynamic scoping on programming is profound. So when dynamic scoping is used, the current attributes of non-local variables visible to a program statement cannot be determined statically. So furthermore, a reference to the name of such a variable is not always to the same variable. Okay. So a statement in a subprogram that contains a reference to a non-local variable can refer to different non-local variables during different executions of the subprogram. So that is the problem with this dynamic scope. So several kinds of programming problems follow directly from dynamic scope. So first, during the time span beginning, when a subprogram begins its execution and ending when that execution ends. The local variables of the subprogram are all visible to any other executing subprogram, regardless of its textual proximity or how execution got to the currently executing subprogram. So there is no way to protect local variables from this accessibility. Subprograms are always executed in the environment of all previously called subprograms that have not yet completed their executions. Okay, so as a result, dynamic scoping results in less reliable programs than static scope. And the second problem with the dynamic scoping is the inability to type check references to non-local statically. So this problem results from the inability to statically find the declaration for a variable referenced as a non-local. Then suppose we have non-local variables or accesses to non-local variables in dynamic scoped languages that take far longer access to non-locals when static scoping is used. So that is about scope of this variables.